Now let's try to draw the Newman projection for different conformations of the propane. So this is the model for the propane molecule. Let me write that on a board. So for propane we have CH3, CH2, CH3, as you can see here. And we have planned to look through carbon 2 and carbon 3 bond. So we are looking through this bond. Okay, so to look through this bond, this is carbon 2 and this is carbon 3. This is what you can see. The front carbon has 2 hydrogens attached to it. They are going to the sides and down, and 1 methyl group attached to it that is going up. So to draw the first Newman projection, let's draw a circle. This point showing the front carbon. Let me number that. 1, 2, 3. So this is carbon 2. 2 hydrogens attached to it, and 1 methyl group. So Me, or methyl, is the abbreviation for CH3 group. So, and we also have CH3, CH2 group. We sometimes abbreviate that as ethyl. Now, so we draw the groups attached to the front carbon. To the back carbon, we have 3 hydrogens attached. 2 of them are going to the sides and 1 of them pointing down. So again, draw out of circle. Okay, so this is the first conformation, the Newman projection for the first conformation of the propane. And as you can see, these groups are not eclipsing one another, so this is a staggered conformation. Now to draw the next conformation, you need to rotate the molecule for 60 degrees. Okay, so I am holding the front carbon stationary and I'm rotating the back carbon for 60 degrees. So this is what we see, all right, after rotation. So the front carbon didn't move. Keep the front carbon. Okay, 2 hydrogens attached to it and a methyl group. Now the back carbon, 3 hydrogens attached to the back carbon, and they are eclipsing the front group. So we draw them all. All right, so now this structure is the eclipse structure for propane. You can again rotate the molecule, okay, for 60 degrees, and again you get the staggered conformation, similar to the staggered conformation that we draw here. Okay, so now energy wise, again eclipse conformation is less stable than staggered. The cost of energy for HH eclipsing is 4 kilojoule per mole. We have 2 of them. And for hydrogen methyl is 6 kilojoule per mole. So overall energy cost is 14 kilojoule per mole here. So the energy difference between the staggered and the eclipsed is 14 kilojoule per mole stagger is 14 kilojoule per mole, more stable than eclipsed. Now the energy diagram is also shown here. So to follow the energy diagram and see what's happening, I am switching one of the hydrogens, connected here. Okay, there we are. All right. So this is the red hydrogen. Hopefully you can see it. Yes, now it is easier to see. All right. So we start from this position where the dihedral angle is 0 between these two groups. And you can draw the structure, the methyl and hydrogen. They are eclipsing one another. Then if you rotate that for 60 degrees, you get the staggered conformation. Methyl is to the top and the red hydrogen is right here. Again, you can rotate that another 60 degrees, gives you this conformation, which is drawn here. And you can also rotate that for another 60 degrees. So the methyl is to the top, the red hydrogen is right here. Now you can keep basically rotating the molecule to get back to your start point. But as you can see, all of these eclipsed structures are identical because we know that. Well, I just marked the hydrogen for you to be easier to follow, but this is hydrogen, this is not another atom. So all of them are identical and they are less stable than the staggered form for the propane. Now let's look at the different conformations for butane molecule using the Newman projection. Butane has 4 carbons, as you can see here. So let me draw that on a board. We have CH3, and if I number the carbons, it's 1, 2, 3, 4, and we have planned to look through the bond between carbon 2 and carbon 3. So this is carbon 1, 2, 3, 4, and we have planned to look through this bond. So if I rotate the molecule, this is what you can see. So this is the front carbon and this is the back carbon. All right. So the front carbon has 2 hydrogens attached to it going to the side and 1 methyl group attached to it. So let's draw what we see for the first conformation. Okay. 2 hydrogens to the side and 1 methyl group to the top. And the back carbon, it has again 2 hydrogens. They are going to the side but to the top, and 1 methyl group coming down right here. Okay, so 2 hydrogens and 1 methyl group coming down. So again, these groups are not eclipsing one another. So this is one staggered conformation for butane. And this is the specific staggered conformation where the methyl groups, the angle between the methyl groups is 180. So as you can see here, this is the angle between these two groups. It's 180. They are as far as they can. We call that a specific one anti-conformation. And this is the most stable conformation for butane. So to get the next conformation, you need to rotate the molecule for another 60 degrees. So I hold this front carbon and I rotate the back carbon. This is what we can see. So the front carbon didn't move. And the back carbon, we have methyl group here and 2 hydrogens in here. So this is a methyl group and 2 hydrogens. So in this structure, the groups are eclipsing one another. So this is eclipsed conformation. Now, the energy between hydrogen and methyl is 6 kilojoule per mole. Between hydrogens is 4 kilojoule per mole. And right here we also have 6 kilojoule per mole. So the overall cost here is 16 kilojoule per mole. Now, we can rotate the molecule another 60 degrees. Okay. So if I rotate, hold the front carbon stable and rotate the back one, I get to this structure. Okay. So hydrogen, hydrogen, methyl. I have 1 methyl here and 2 hydrogens here. So this is a form of a staggered conformation, but this specific one, this is a staggered. The basically groups are not eclipsing one another, but these methyl groups are very close to one another, so they still have an interaction, and that interaction costs about 3.8 kilojoule per mole. And this specific staggered structure, we call that gauge structure. So that one was anti, this one is gauge. Again, you can rotate the molecule another 60 degrees. Okay. So if I rotate that, okay, I get to this eclipse structure where the methyl group, 2 large group eclipsing one another. So that would be more unstable, higher in energy. This is actually the highest one, the most unstable eclipsed conformation. So this is also eclipsed. Now, if you look at the energy diagram that shows energy against the dihedral angle, so we can start from this conformation where the methyls eclipsing one another. It is right here, and you can see it's very high in energy. So if you want to calculate the energy here, the eclipsing for hydrogens is 4 kilojoule per mole. We have 2 of them. And the eclipsing for methyl, it's been reported that it is about 11 kilojoule per mole. Now, if you rotate the molecule for 60 degrees, you get to the staggered conformation, and it is gouge. This is the specific one. This is a gouge conformation where the methyl still have interaction with one another right here. Okay. And if you rotate the molecule one more time, you get to the eclipse conformation, but this is more stable than the first eclipse because the atoms are still eclipsing one another, but not two large group like methyl. So we get that one. And if you rotate one more time, we get to the most stable conformation for the butane, where two methyls are anti to one another, which is right here. You can keep rotating to get to the basically start point, but butane has 4 conformations itself. Now we want to try and convert the Newman projection to the bond line structure. There are a couple of ways that you can do it. The first one would be to have your model kit and make the model of the molecule by looking at the Newman projection, and then rotate the model in the 3D space and draw the bond line structure as you can see it. The second way is to not use the model, and this is the way that I would like to teach you, because if you are taking MCAT and PCAT and they want you to convert the Newman projection to the bond line structure, you may not have access to the model kit. So this way is pretty easy. There are a few steps that you need to follow. The first one is to draw a line first. Now I would like to color code all the atoms in this Newman projection. So the front carbon, I show that in blue, and the groups attached to it are also show them in blue. Then to the back carbon, so I cannot show the back carbon, however I can show the groups, and I show them with red. Okay. Now, on this line that you draw, the blue carbon would be in the left, and the order is important. The red carbon, which is the back carbon, would be in the right. Then what you need to do, you need to draw a line passing through this circle. So any atoms that are placed on this green line, they are placed in the plane of the page. Therefore, I can draw 2 lines. To carbon blue, I have 1 methyl group attached, which is on this green line, meaning that it is on the plane of the page right here. And to the back carbon, I have 1 methyl group attached, which is also in this green line, and it is on the plane of the page. Okay. Now, after drawing this, any groups that are in the left, they are going into the plane of the page, and any groups that are in the right, they are coming out of the plane of the page. So let's draw them. To carbon blue, right here, I have hydrogen attached, which is going into the plane of the page, and to show it, I can use the dash bond. To the same carbon, I have OH attached, which is coming out of the plane of the page, and I can use wedge bond to show this. To the back carbon, I have bromine attached, which is going into the plane of the page. And I also have a hydrogen attached, which is coming out of the plane of the page. And I show it with a wedge bond. So this is how you can convert a Newman projection to the bond line structure. As I mentioned, you can also simply make the model of the molecule by looking at the Newman projection and then draw basically the bond line structure by looking at the model. So here is the model of this molecule. If you look through the model, through these two carbons, this carbon and this carbon, that one is my blue carbon, which has a methyl group attached, which is going upward, OH group attached, which is going to the side, and the hydrogen attached, which is going to the left and to the side. And to the back carbon, I have hydrogen attached, bromine attached, and one methyl group attached, which is coming down. So to draw the bond line structure, what I can do, I can simply rotate the molecule and draw what I see. So if you imagine there is a plane passing through the molecule, all of these atoms would be on a plane of the page. And this is what we draw here. Then I have OH group coming out of the plane of the page, attached to the blue carbon. I draw that here. And hydrogen also coming out of the plane of the page, attached to the red carbon, which we draw here. So to the blue carbon, I have hydrogen attached, which is going to the back, right here. And I show that with dash. And to the red carbon, I have bromine attached, which is going to the back. So you can also simply make the model and look at the bond line structure and draw what you see.